Alright guys, so in this lecture what we are going to look at is the titration experiment specifically for PCH 221. Now I'm going to basically start like explaining everything from the basics, which is the foundation, but I'm not going to waste a lot of time. I'll just define what standardization is, what titration is, what a primary standard is, and then what a secondary standard is. Now listen, here's what we call standardization. Now when we talk about standardization, what we mean is knowing the exact concentration of something. Are you getting it now? Determining the exact concentration of something, or the process of determining the exact concentration of something, is called what? Standardization. And that is the basis of all titration. All titrations are standardization. That is, you are trying to determine the exact concentration. You are trying to determine the exact concentration of something. All right. Now, what are some of the units of concentration? From what we know that concentration can be in gram per mil. It can even be in gram per deciliter. It can be in mole per dm cube, etc. Are you getting it now? So the process of trying to determine the exact, please emphasis on exact, concentration of anything is what we call what? Standardization. Is that okay? Now when we talk about the concentration, what do we mean? We mean the amount of substance in a particular solution. Is that okay? That is what concentration is. For instance, if you have, let's say, a class of the same size, let's say this size 1 and size 2, these two classes are of the same size, and then you have 10 students here, and then here you have 20 students. Now you are going to say that class, if this is B and this is A, you can say that class B is more concentrated than class A. Why? Because there are more persons in class B as compared to what? Class A. Is that okay? So that is generally what standardization is. The process of trying to determine the exact concentration. So for instance now, if I want to determine the exact concentration or the exact number of people in class A, that process of me trying to determine that is what we call what? Standardization. And one of the methods of standardization that is often employed is the method of what? Titration. Now, what is titration? Generally, in titration, what you are trying to do is to know the exact concentration using comparison. Using what? A comparison with what we call a standard. Using comparison with what we call a standard solution. Now the question now is, what is a standard solution? A standard solution is that solution with accurately known concentration. Accurately known concentration. You call that what? A standard solution. Are you getting it now? You call this a standard solution. Now, for instance, let us say this is a standard. Let me just give you an analogy. Let's say this is a standard. Let's say this is a standard. Now, if you look at the length of this thing very well, the length of this is 5. This 5 here is the standard. I'm trying to make an example for you and how titration is actually done. Now you have the standard, which is of course 5 centimeters. Now if I take something here and then take it to half of this, now without me telling you the concentration of this one, or let me say without me telling you the height of this, now you should be able to determine the height of this one from this. True or false? Why? Because you know that this one is what? 5 centimeters. This one is accurately what? Known. Now when you compare it with this one, this height here is like half of this. True or false? So if this one is 5 centimeters, it means this one will be how many centimeters? 2.5 centimeters. Is that okay? Now this thing here that is used to compare, what you have here is what we call the unknown in titration. Why this one here is what we call the what? the standard. Are you getting it now? The standard, you know the height of the standard, which is 5 centimeters, but you don't know the height of the unknown. But when you place the unknown close to the standard, there's some similarity. The similarity is that the unknown is like half of the standard. The standard is accurately known. That is why we say a standard solution is a solution whose concentration is accurately known, so you know the height. But by comparing it with the unknown, you are able to get the concentration of the unknown, which is about what? 2.5. Is that okay? So that is the general idea of what titration is. Now, we have two types of standard in titration. How many types of standard? 2. Now, the two types of standards we have in titration, we have what we call primary standard. All right? And then we have what we call what? The secondary standard. Is that okay? We have what we call the primary standard, and then we have what we call the what? The secondary standard. Now, what is the difference between the primary standard and the secondary standard? Now, listen. The primary standard is a standard of very high purity. Very high what? Purity. And the concentration is accurately known. Is what? Accurately known. This standard here is what we call what? A primary standard. It has a very high purity. That means it's very pure. And the concentration is what? Accurately known. And because it has high purity and the concentration is accurately known, you can actually use it, or you can compare it with an unknown. Are you getting it? To get the concentration of the what? Unknown, based on some relationship between the primary standard and the what? Unknown. Is that okay? That's what is called a primary standard. Now, what is a secondary standard? Now, secondary standard, they are standards that are used for titration also, but they are not that pure. Are you getting it now? Their purity is in question. Do you understand? Their purity is in what? In question. Now, but that is what you want to use to get your what? Unknown. Now, you want to use this secondary standard to get your unknown, but the purity of the secondary standard is what? Under questions. For instance, let us say you have this one, the height here. Let's say this height is under question. You don't actually know the exact height. Are you getting it now? In such a way that even if I put half of it here, let's say half here, let me use half. That half, you won't be able to tell. Why? Because you don't know the what? Exact measurement here. So what do we normally do to secondary standard? We use the primary standard to get the exact concentration of the what? Secondary standard. Is that okay? So what we normally do is to use the primary standard, which we know accurately, to get the exact concentration of the what? Secondary standard. Are you getting it now? So for instance, let me give another instance now. Let us say this is our primary standard. I'm just trying to use lines to explain so that everybody will understand this stuff very well. Let us say this whole thing here you have is your what? Primary standard. Secondary standard, do you know it? No. Okay, let us say this is our secondary standard. Secondary standard is about, let's say, something like this. But the primary standard is accurately known. The primary standard is what? 8 centimeters in this case. I'm just trying to say, talking about height, using height to explain. Is how many centimeters? 8 centimeters. Secondary standard. With the primary standard now, you will now be able to get the secondary standard. What is the relationship between them? Is that this one here is like half of this, right? So it means secondary standard now will now be what? 4 centimeters. Is that okay? So you can now use this secondary standard to what? To calibrate another compound. True or false? If let's say this is the unknown you want to look for. Let's say this is the unknown you want to look for. Now, what do you think will now be the concentration of the unknown? It will still be what? 4. Are you getting it now? Because their ratio is that they are the same, like 1:1, they are the same thing. Do you understand? So that's the general idea. So whenever you are given a secondary standard, it means you are going to look for a primary standard to standardize what? That secondary standard. Are you getting it now? So this first one here is what we call the what? Primary standard. This one is the what? Secondary. And then this one is the what? Unknown. So if you are given a secondary standard, you have to use a primary standard to standardize the secondary what? Standard. And then use the secondary standard now to now get the concentration of the what? Unknown via some comparison. And the comparison that is mostly made in most cases is their mole ratio. Is their what? Mole ratio. For instance, if let's say this is the concentration here, let's say this is a particular compound given, and this is a particular compound, and I give you 1:1, the molar ratio, it means that both of them will have the same height, true or false? Now, what do you think is the molar ratio between this one and this one? 2:1. Are you getting it now? So the molar ratio actually gives you an idea of the what? Of what you are to do. Now, the primary standards that are usually given that we know very well using titration experiment is sodium what? Triazocarbonate. Is sodium what? Triazocarbonate. But there are other primary standards. Now, most times, if they give you a primary standard, that means the one that the concentration is accurately known. Your factor for that calculation will be how many? 1. That means a situation where they say, don't standardize. You are not standardizing anything, just calculate. Your factor must be how many? 1. Is that okay? So now we've been able to distinguish between primary standard and what? Secondary standard, and also what standardization is. Are you getting it? And how we can use standardization to get unknown. Now, let us go straight to what the titration is all about. Now, let's say you have, most time the titration setup, it usually involves something in a burette, right? Which of course, everybody know you have something in a burette, which is the what? Unknown concentration most time, but not all the time. And then you have, what do you have here? Your what? Conical flask. Is that okay? Now, this one, you know the volume of this. Let's say 10 ml. But the concentration of this, do you know it? No. But here, you know the concentration. Let's say 0.1 molar. And also the volume is the titer value you get from this experiment. True or false? Are you getting it now? The volume is the what? Titer value you get from the experiment. Let's say your titer value is, let's say 10 ml 2. If you use the equation CAVA all over CBVB is equals to NA over NB. Let's say what you have here is your what? Acid. And what you have here is your what? Base. Let's just say. Or in situation where you have, let's say sodium hydroxide is your base. While here is your what? Acid. What is your mole ratio? Mole ratio is what? For sodium hydroxide reacting with ACl, what is the mole ratio? Mole ratio is like 1:1. True or false? If you write the equation of reaction, what you are going to have is sodium chloride plus what? H2O. Mole ratio here is 1:1. That means Na is 1, Nb is what? 1. You know C, you don't know Ca, which is the concentration of the acid. Is that known? No. So from here, you can say Ca, which is what you are looking for, times Va. The volume of acid is the volume you measure, which is how many? 10 ml. I'm just using this as hypothetical. Cb is the concentration of base. It will be given 0.1 mole times the volume of base is your titer volume. Let's not make things 10 ml. Let's say your titer volume is like 5 ml here. So your titer value here will be what? 5 ml. That means the volume you get from the titration experiment. Right? Are you getting it? Now, another thing that you also need to take note is that what is up here must never be base. It can be acid. What is here must never be acid. It can be what? Base at any point in time. This will be equals to Na is what? 1:1. So from this, you'll be able to calculate the concentration of the acid that was actually used in this experiment. Is that okay? So that's the general idea of what titration experiments. Then we are going to look at how to calculate for milli equivalents and co. Now, what we are going to do is we are going to use this experiment to practice some questions and how to calculate for milli equivalent and co. Now we have an experiment which is direct titration of weak acid. Now the question says weigh out accurately 20.0 gram 10 ml of 5% vinegar in a small stopper sample bottle. Transfer it to 100 ml volumetric flask. Rinse sample bottle with 50 ml distilled water and make up to volume with distilled water. You measured how many gram? 20 gram. You transferred it into what? 100 ml. Out of this, you prepared 25 ml. Are you getting it? Into what? 100 ml flask, and add 5 drops of phenolphthalein and titrate with 0.5 molar sodium hydroxide. That means the reaction is between what? Vinegar, which is what? Acetic acid, and what? 0.5 molar sodium hydroxide. Because all this preparation you did here was to prepare for what? Vinegar. Are you getting it now? Reacting it with how many more sodium hydroxide? 0.5 molar sodium hydroxide. Say, read the first shade of permanent pink. Now, note, phenolphthalein is colorless in acid solution, but pink in what? Base. So the end point, you are going to get a pink color. Calculate the acetic acid content of the vinegar and express your result as percentage weight by weight of acetic acid. Now, the first thing you need to do for any titration experiment is to run your titration and then get your titer values. Are you getting it now? When you must run your titration, the titration is between what and what? Between acetic acid and what? Vinegar. I mean, between vinegar, which is acetic acid, and sodium hydroxide, which is like an acid-based titration. Now, these are the titer values. Now, having gone to your titer values, first of all, you do final reading, initial reading, volume of titrant used from your titration, second titer, first reading, second reading, and then volume. The next thing you are now going to do here is the average volume of sodium hydroxide used, because the titrant in this case, average volume of sodium hydroxide. The titrant in this experiment is what? Sodium what? Hydroxide. Is that okay? Average volume of sodium hydroxide will now be what? 29.10, which is first titer plus second titer divided by 2. What do you think that is going to give to us? First titer, can't see there, 29.10 plus 28.60 divided by 2. This will give us 28.85 ml. So it means the average volume of sodium hydroxide used, which is your titer value, is what? 28.85 ml. Is that okay? Now you are now going to come here to start your calculations proper. All right? You are going to come here to start your calculation proper. Now, what are you going to do? It's very easy. First of all, you write your equation of reaction. The equation of reaction is between acetic acid plus what? Plus sodium hydroxide. Acetic acid plus sodium hydroxide. Now, if you write this, the equation, the balanced equation, you are going to have the balanced equation is going to give us this, react with this, is going to give sodium ethanoate plus water. So you come here at the corner and write your titer value. What was the titer value? I'm just going to write it here. Titer value is what? 28.85 ml. Are you getting it? 28.85 ml. Now, what is the titer value giving us? It's giving us the volume of what? Of what used? Sodium hydroxide. Are you getting it? That reacted. Is that okay? The titer value is giving us the value of sodium hydroxide that what? Reacted. Now, the next thing we have to do in this experiment is to calculate our milli equivalent. Now, listen. When you are calculating for your milli equivalent, some of you don't know this, especially the year 2 students. When you are calculating for your milli equivalent, there are certain things that you must take note of. Now, one of those things you must take note of is the concentration of the titrant. What was the concentration of the titrant? The titrant is what you use to titrate sodium hydroxide. What was the concentration of sodium hydroxide given here? 0.5 molar. Are you getting it now? Sodium hydroxide. So you come here and write that somewhere here and say concentration of titrant, concentration, or you can just write it, the time instead of titrant, concentration of sodium hydroxide is what? 0.5 molar. Is that okay? Now this 0.5 molar now is what will actually guide you on what to use here. Now the only thing that you are so concerned about here is these two reactants, which is acetic acid react with what? Sodium hydroxide. Is that okay? That is the only thing you are so much concerned about, not even any other thing here. Now, and another thing that you must also take cognizance of is their molar ratio from the balanced equation. The molar ratio here is what? 1 ratio what? 1. Are you getting it now? So it means you can come here and say 1 mole of acetic acid react with how many moles of sodium hydroxide? 1 mole sodium hydroxide. Is that okay? Now, what is the mass of 1 mole of acetic acid? Is it 60 grams? Carbon is how many? 12 plus hydrogen is 3 plus carbon 12 plus 32 plus 1, which is 36 plus, are you sure it's 60? This, okay, yeah, 12 plus 12 plus 15, then this is 17, 18, 7, no, yeah, 20, this, okay, 60 point what? Something. 60.05 gram. There's one of the this that has 0.5. 60.05 gram of what? CH3COOH. But approximately 60 gram. But you'll be given that is 60.05. Sometimes they may give you the milli equivalent, but most times they will not give it to you. You have to find it by yourself. So you can say that 60.05 gram of ethanoic acid, which is vinegar. Vinegar is ethanoic acid, in case you don't know. Reacts with how many mole of sodium hydroxide? 1 mole. But you know that molarity is what? Number of moles over what? Volume. Number of moles will be what? Molarity times what? Volume. Right? Now, because you have 1 mole here, 1 mole is the number of mole. It means your molarity must be 1 and your volume must be what? 1 liter, because 1 times 1 is going to give us what? 1, which is the number of mole here. Now, had it been the number of mole here were to be 2, it means either your molarity will be 2 and your volume will be 1 liter, or the molarity will be 1 mole and the volume will be how many liter? 2 liter. But for this one, since the molar ratio here is 1, you can just say this will give us 1 mole, 1 liter is approximate to what? 1000 milliliter. Are you getting it now? 1 liter, 1000 milliliter of what? Sodium hydroxide. Is that okay? Now, the next thing you now start to do now is to divide. Now, what was the concentration of sodium hydroxide you reacted with from what we had here? Concentration of sodium hydroxide here is what? 0.05 abi? Molar. So you come here and divide till you get 0.5 molar. Now, what do? Divide here by what? 2. And then divide here by what? 2. Now, this will give us what? 30.025 gram, abi, of acetic acid. Will give us 0. What? 1 divided by 2 is what? 0.5 molar, 1000 milliliter of what? Sodium hydroxide. Are you getting it now? Now listen. You are looking for the milli equivalent. That means the mass of acetic acid that will react with 1 mole of what? Sodium hydroxide. Now what do? We divide here by 1000 to get 1 mole. Milli equivalent means you must break this 1000 mole to what? 1 mole. And to do that is to divide here by 1000. Whatever you are dividing here, you must divide here. When we divided 2 here, you must divide this by 2. So, and you cannot divide this and divide this. You divide 1 here, divide 1 here. Now, at the end of the day, you have to divide here also by what? 1000. So what will this give to us? This cancel this. This cancel this. This is going to give us what? 0.0 what? 30 another 0.25 gram of acetic acid. We react with how many mole? We react with 0.5 molar solution, but this will react with 1 ml of what? Sodium hydroxide. Now listen, the interpretation of this, listen, is that 1 ml of sodium hydroxide, right, we react with what? 0.030025 gram of acetic acid. That is the molecular interpretation. 1 ml of sodium hydroxide, 1 ml of what concentration of sodium hydroxide? 1 ml of 0.5 molar sodium hydroxide will react with what? 0.325 gram of what? Acetic acid. Now you can decide to write this and just say 1 ml of sodium hydroxide, right, we react with what? We react with 0.030025 gram of what? Acetic acid. Abi? That's your milli equivalent. This is your milli equivalent. You are now going to write this and say this is what? Milli equivalent. Are you getting it now? 1 ml of sodium hydroxide of what concentration? 0.5 molar. That is what you use for your titration. We react with what? 0.03025 gram of acetic acid. Now, what was the titer value that you got for sodium hydroxide? The titer value was 28.85 ml. So you are now going to come here to get the amount. If 1 ml reacts with this, that means 28.85 ml of sodium hydroxide is going to react with what? X, right? And then at this point, you can what? Cross multiply. This multiplied by this will give us X. Ml can cancel what? Ml. Are you getting it now? Sodium hydroxide can cancel what? Sodium hydroxide. So X will be equals to 28.85 times 0.030025 gram of acetic acid. What did that give to you?
0.86.
It's your calculator when no they show. Which is X is equals to what? 0.8662 gram of acetic acid. So it means the real amount of acetic acid that was in that 20 ml was what? 0.8662 gram. I'm going to show to you. Now, this is one way to solve it. But the one that you have in your manuals and the one that we'll be following is the one that we are now going to say calculated weight, or we are going to say the experimental weight or the calculated weight is equal to calculated weight. There's a formula that you guys usually use. You say calculated weight is equals to what? Milli equivalent times what? Titer value times factor. The reason why I have to explain it this way is so that you actually understand what you are doing. Now, what was the milli equivalent that we calculated was what? 0.030025 times the titer value is what? 28.85 times the factor. I told you that if you are not standardizing twice, that means if it's a primary standard that is given to you, sodium hydroxide that's used here, you know the exact concentration of it. It was given as 0.5 molar, right? So that one, it means that the factor will be what? 1, right? Now, when you multiply this, what is that going to give to you? It's still going to give us what? 0.8662 gram of acetic acid. Are you getting it now? So this is the amount of acetic acid that was present in the 25 ml that you actually pipetted and titrated. Now listen, what this one means is, if you read the practical, what did you titrate with? Listen, it say pipette 25 ml of this entire, it say weigh out accurately 20 gram of 5% vinegar into a small stopper sample bottle. Transfer it to 100 ml volumetric flask. This will not concern you. Rinse sample bottle with 50 ml distilled water and make up to volume with distilled water. That means, listen, it means 20 gram, put it into a 100 what? Ml volumetric flask. Rinse the sample with 50 ml distilled water. That means you should be rinsing and make up to volume. Make up to which volume? Make up to the 100 ml. Are you getting it now? So it means that 20 gram is present in how many ml? 100 ml. Is that okay? Now, they say pipette 25 ml into a conical flask. This 25 ml that you pipetted was what we titrated now. And the amount in the 25 ml is this 0.8662 gram. Is that okay? The amount of acetic acid in the 25 ml is what we calculated to be what? 0.8662 what? Gram. But what was given initially was, if you look at it very well, they say 20 gram was initially present in how many ml? 100 ml, right? Now we want to know the concentration that we should be expecting, or the actual concentration that we should be expecting, and that would be what? 25 ml, because this was what we actually titrated in the 25 ml. If 20 gram give 100 ml, it means 25 ml will give us what? X, right? Cross multiply this, multiply by this times this is going to give us what? 100x is equals to 20 times 25. Divide both sides by 100. What would that give to us? Is that going to give us 5 gram? 5 gram. Now, but in the experiment, listen, the experiment you guys did, you didn't use 25 ml. This one was what the textbook speculated, but you didn't use 25 ml. What you actually used was what? 10 ml. So this will be, in place of this 25 ml, what are you going to have here is what? 10 ml. Is that okay? 10 ml, not the 25 ml. That was what people used in the experiment, not the 25 ml here. So you have 10 ml. So 20 times this divided by this, X will be how many gram? 2.0 gram. All right. So this is the actual weight that you were expecting. This is the beauty of what? Titration. This is the what? Actual weight. But when you calculated, what did you get? 0.8662. That means after your titration, what you got was what? 0.8662. Now the titration one is the correct one. Are you getting it now? So you've been able to use sodium hydroxide. All these processes we are trying to do since is we've been able to use sodium hydroxide to get the exact concentration that was in what? In the 10 ml, not 25 ml now, because what they say pipette 10 ml, not 25 ml. The manual say pipette 25 ml, but what you guys used in the practical was what? 10 ml. Are you getting it now? So when we were actually expecting how many gram? 2 gram. Because if 20 gram is present in 100 ml, it means 10 ml will be present as what? X. Are you getting it? It was this 10 ml that we titrated that gave us the mass to be what? 0.866. And this 10 ml, we also did the normal calculation and it gave us what? 2.0 gram. So it means we were actually looking at 2.0 gram as the real mass, but in the real sense, there are impurities that are present in this 2.0 gram. The amount of acetic acid present there, the correct amount is what? 0.8660. Is that okay now? Now, at this point now, you cannot calculate your what? Percentage purity. Is that okay? So what do you think will be the percentage purity now? Percentage purity will be equals to what? The this is the weight we are actually looking for. You can decide to do whether actual weight and calculated weight. You can decide to say calculated weight or all over what? Actual weight times what? 100%. Anything you want to use to represent this, or you can say the experimented weight all over what? The actual weight times 100%, which will be what? 0.86 what? 62. Are you getting it? 0.8662 divided by what? 2.0 gram. Is that okay? Now, what do you think that is going to give to us? This cancel this. Times 100%, right? Times 100%. What is that going to give to us? 43 point what? 21%. 42.31%. So this is the amount of what? This is the percentage purity of vinegar. And I think that is the only question that is here. Express your result as percentage weight by weight. So your result now will be 43.31% weight by what? Weight. Are you getting it now? So that is basically that for this one.
Seen in 100 grams.
See the 20 gram from the experiment it was given to you. Weigh out accurately 20 gram.
Okay, in 100, in 10.
Of 5% vinegar. This is just the concentration of vinegar in a small stopper sample bottle. Transfer it to a 100 ml volumetric flask. What is volumetric flask used for? For preparation of standard what? Solution. Rinse sample bottle with 50 ml distilled water and make up to volume with distilled water. Make up to with volume to the 100 ml. So it means that you actually have 20 gram in what? 100 ml. They say pipette 25 ml into a 100 ml flask.
Okay, that
But this
100 ml
pipette
flask,
25 ml now, I'm not telling you that what you use for your practical is what? 10 ml.
Okay, that's
Are you getting it? Into a 100 ml flask. This 100 ml flask, it means you just prepare into this 100 ml flask. It does not mean you should make it to volume. Are you getting it now? So therefore, if 20 gram contain 100 ml,
how many will 10 ml contain?
10 ml will contain dash. You calculated this and it gave us 2.0 gram. That's what it gave us. We kept it at the corner. We can't carry this 10 ml now. Can't go titrate am with sodium hydroxide. It can't give us a different value of 0.8662. It means there are impurities that will actually bulk up this 0.8662 to give us what? 2.0 that you feel you have there. Are you getting it now? So titration now has been able to give you the exact concentration. That's why we say it's what? Standardization. Is that okay? So that is that.